Welcome everyone to another OCP Tap call. This is call number 161. I'm pleased to introduce our speaker, Greg Armstrong, Principal System Architect at the Timing Division at Renaissance Electronics. He has spent more than 30 years in telecommunication industry with deep experience in system architecture, application engineering, embedded software, and timing technologies. For more than 19 years, he has focused on synchronization, including frequency, phase, time distribution over packet networks. Greg presents Renishaw in several key standard groups, including the IEEE 1588, IEEE P3035, and the ITU-T SG15 question 13. He's also active in broader timing community through the WSTS steering committee and the ITSF advisory board. Today, Greg will present embedded pulse per second, or EPPS, a physical layer approach for embedding a precise 1 second phase marker directly into a 10 megahertz reference. So his talk will cover how this technology can help reduce cabling complexity, minimize skew, and simplify deterministic timing distribution in dense infrastructure environments such as a rack, server, data center, and edge sites. With that, I'll hand it to Greg. Greg, thank you for joining us. The floor is yours.
Thank you very much, Amit. Yes, good afternoon, morning, evening, everyone. Thank you for the introduction and thank you for the invite to talk today. So yeah, as highlighted, I'm going to talk about a single interface that can be used for both phase and frequency distribution. You might see in similar talks or references throughout other TAP talks, or those have attended some of the OCP Global Summit and some of the breakout sessions. There's been some discussions around these topics. So, I'll go through the slides. I got a few slides here to expand on a lot of the stuff I've maybe talked about in the past, to expand on some of those ideas, a little bit more technical, a little bit more details about what does that mean, and also highlight, references that are already highlighting the need for this type of interface. The timing demand in data centers, I don't think this is going to be new to anyone here on the call. These are things that have been brought up to the project group over the years of saying, we definitely are seeing there's going to be a need for precision synchronization, precision time needs within the data center, within the server, for distribution amongst data centers. And because of this, these timing constraints are well beyond what we can get with standard technologies such as the NDP protocol to distribute time, which you might get milliseconds or maybe sub-milliseconds with some hardware aiding, to other distribution mechanisms that are used today. And also internally, the server has historically not really been built to look at clock distribution, more at providing clocks that might be needed for the PCIe bus and things like that. And typically a one-way, right, is pushing the clock maybe from the host out type of thing, but rarely was it ever taking a clock coming in to actually use it within the server itself. So those are some of the discussion points that I'll talk about. And before I jump into it, I wanted to highlight, there's been talks about this. Those that were at OCP Global Summit a couple of years ago, I guess almost 3 years ago now, I gave the concept of the synchronized NIC, saying, we're starting to get synchronization into it, but where there's very little means of getting it through. And then the introduction of the time card, kind of the same thing. You look at a lot of the diagrams, it was very difficult to distribute the signal or the timing to other cards or throughout without complex cabling and other aspects. So what I wanted to present was some of the things that have been advancing within the PCI SIG and also within the OCP community, and talk about some of those things. I guess preference would be hold off any questions, hopefully to the end. But if there's something you really want to interrupt and talk about, feel free to say something as well. And the other thing I wanted to highlight is this came right from one of these discussions here from Jason Rock a couple sessions ago. He highlighted like the challenge, right? Like again, most of the distribution today has been looking at distributing concepts like a 1 pulse per second for some sort of 1 second alignment or precise measurement capabilities using cabling. And he highlighted in his presentation like the complexities, right? These are typically customized coax cable. They are very firm and rigid, very difficult to maneuver. And you can appreciate that this is just showing two 1 PPS signals going between cards. But imagine if you're trying to do it between racks or even between distances of buildings trying to distribute this information. And so my focus isn't more about the distribution outside or let's say beyond the top of rack, but looking more at how do we actually take advantage of using that clock within the server, within the rack itself. So what are some of the limitations? And again, a lot of these things I think have been discussed over the sessions, talking about, one of the biggest disadvantage when you start distributing any sort of signal, let it be a frequency clock like 10 megahertz or a 1 pulse per second that may represent some sort of phase or alignment relationship, is that typically these have to traverse paths to get there. And a lot of this is using historically traditional means, right? Trace is directly on the board or cabling. They go through connectors to get from one card to another within the server and things like that. And all of that starts accumulating some sort of error in that distribution. And as you start accumulating that, it can be quite large in the tens, if not hundreds of nanoseconds. And it can also be different between different cards, even though it's all contained within the same server system. So it becomes almost unavoidable. You can't avoid it. You could try to compensate it out and do things, which is allowed. But the challenge is, especially if you have more than one signal that you're trying to distribute, is you have to do that on all the signals to do that type of compensation. And so the presentation I'm talking today is introducing a concept of saying, well, what if we were able to kind of combine some of this information so that instead of using more of the traditional way of doing phase and frequency distribution, could we do it much more efficiently with much more better precision and take advantage of existing capabilities for that clock distribution that's already available and used today? So it's not introducing new technology per se, but maybe just a concept of these embedded markers to give us additional information about that clock signal. And this is just a simple comparison, right? Like and a lot of this you can understand is like I talked about the cable trace mismatching, cable connector variation, right? Even going over connectors, there's variations in terms of skews. Routing it throughout, you can accumulate it. And a lot of that may need calibration, and that calibration for multi-signals becomes more complex, more costly, and it's not very scalable. As Jason Rock highlighted in his, right? Like very difficult to scale a system like that if you have to start distributing more and more signals across the rack, or even internally trying to physically connect cables between cards within the server itself. You'd have to dismantle it, open it up, and then start putting these cables into play. So what we want to try to determine is how can we make this all a little bit easier, make it more of a common mode so that any calibration you do is applicable to both signals. How can we maybe make it a little bit more deterministic because we are only looking at a single signal and things like that. So those are some of the stuff that I'm going to talk about today. So, why is this being discussed? And it's not a new discussion. Jason Rock highlighted some of the work that was done in the OCP NIC project for 3.0, talking about trying to distribute clocking. Used kind of more traditional telecom concepts of clock distribution, where there was a separate frequency clock, a separate sync signal clock, and maybe bidirectional, one going off the NIC, and one coming back into the NIC for very basic clock distribution, which is doable and uses a lot of the similar technologies that are available today. But one thing that they did introduce is they made a mention of, hey, well, you could also, instead of just doing a 10 megahertz frequency, you can do an embedded pulse per second, but not really expanding on what did that mean. But just kind of highlighted that, hey, technology term has been around. Some people know, vendors know how to do it, some may not. Those that do, those are probably who you're going to use. So, not great a way of introducing clock distribution because, there's not a lot of, uh, you know, uh, strong take on it. It's very difficult to convince people to use proprietary silicon, proprietary cards, proprietary means of doing it. Even if the interface is maybe open, it just becomes a little bit more difficult. And so the PCI SIG has been looking at this as well, and with their card electromechanical standard in version generation 7, they actually started looking at the exact same concept. But instead of looking at it as a full-fledged clock distribution and having maybe some compatibility with telecom concepts, they just said, you know what, let's just look at what would be the best way to take traditional clocking and some sort of marker alignment and distribute it within the card. And you can see the challenge was highlighted very early. Ahmed, when the early concepts of the time open time server system came about, right? The early diagrams were effectively showing coax cables to connect between cards, right? Because there was no other means to really do it, right? You couldn't find a signal that you could piggyback on to say, oh, let's use this and distribute it from this card to the other card. Or even the host may have access to it directly on the board because it's routing or distributing that clock itself. And so what the PCI SIG-Chem group was looking at is saying, well, how can we build the concept of a clock tree distribution and to distribute both frequency, but even very precise time distribution could be done with this. And basically complement other technologies out there, right? This doesn't eliminate maybe the need for the precision time measurement that's used to distribute a timing signal over the PCIe bus and things like that, but it definitely can complement it, right? When you can start using concepts like synchronization, synchronizing physical layer clocks with the 10 megahertz, or even maybe having a redundant or alternative means of seeing where that 1 hertz marker is because that timing is coming in from a time card itself that you want to distribute within your system. And like I said, this has already been even looked at into the OCP. It's already part of the OCP NIC 3.0 documentation. They talk about how to facilitate support for high precision clocks. Definitely maybe a more complex interface because it's a multi-signal. I think there's like 6 pins they use because they do both clocking, sync. It's bidirectional. They have like a general purpose indicators to pass alarm information over physical wiring. Basically common, very similar to a lot of telecom, which you can tell was very influenced by probably the telecom community when they were looking at how to define that interface. But very similar concept is they looked at, are there any pins available that we could reuse? They call it the flex IO pins, where they maybe repurposed pins that were pre-existing, but the functionality that they were defined for just really don't have relevance in today's connectors and today's cards, that maybe we repurpose those pins for other purposes, but take advantage of existing ways of making sure that that can be scalable. So make sure software can learn information about a card that's plugged in. Does it support that new signaling? And then set up that communication between the host and the card itself. So again, a lot of that stuff was documented and defined in the OCP. But again, a lot of some of the technology terms they use, like EPPS, maybe were assumed that the reader really had knowledge of what that meant. And so again, that was maybe the biggest limitation of it, which maybe is one of the reasons why maybe it didn't get a huge uptick, but it is being used today. I was talking to people at OCP just here in Canada. They had their OCP summit for Canada just last week, and some of them said like we're actually have already been exposed to some of this using it today. So it's not that it's not being used, but I don't think it's as common or knowledgeable, which is why this presentation is really being given, is to try to make sure that is being aware for other groups to start taking advantage of some of this interfaces. So what is embedded pulse per second, right? Again, easy to say the term, easy to maybe kind of picture it in your head what it means, but where is it actually defined? And I think that's probably the biggest thing is it is not defined anywhere, right? So historically, a lot of times when people are looking for definitions, they would look at the large standard bodies to understand how do you define that interface, right? What is PCIe bus? What is the PCIe clock? Oh, let's go to PCI SIG and learn about what that means. Or what is a 10 megahertz measurement clock or a 1 PPS measurement clock that's used for telecom? I'll go to an ITU specification and say, oh, I can read up on that and know exactly what that is defined as. But unfortunately, EPPS, there is no existing documentation today. Hopefully it will get in. Some of that is being proposed. I'm proposing this within the ITUT to look at how do we maybe define it as a new means of measurement distribution, because it does contain information that is redundant between two signals, right? Why have a 10 megahertz that represents your frequency and a 1 PPS that represents your phase, right? So how, again, it makes sense to try to combine this. So even at the telecom level, they're looking at some of these concepts as well. So let's kind of define that waveform. What does it mean? Of course, anytime you talk about embedding something, you have to understand, well, what is it, right? Are you doing amplitude modulation? Are you manipulating the duty cycle? What does that mean? You can't just say you're embedding it, right? So historically, what that concept means for most people is what they call a pulse width modulation, right? They are effectively manipulating the duty cycle of the clock to represent some symbol, like a 1 or a 0, by manipulating that pulse to maybe be a quarter of the width or maybe 3/4 of the width to represent different things. And so by doing that, you can just kind of create a marker within a standard clocking signal, but it doesn't actually, disturb the frequency clock itself. Most of the time when you're distributing a clock such as 10 megahertz, it's a reference clock. It's not itself used to actually distribute, physical data. It's not used directly at a SerDes interface or directly to send something over the wireless infrastructure, right? It's more of a reference clock that will get somewhere else multiplied up to a higher frequency. And so having a distorted duty cycle doesn't really impact it from a frequency clock. That 10 megahertz clock, even with a modulated signal or even multiple modulated pulses, really is not going to have an impact to the ability for a phase lock loop to lock to that clock and resynthesize higher frequency clocks, which I've talked about in other discussions even here about the concept of a phase lock loop and what it does. Typically, the phase lock loop is looking at the rising edge. It really doesn't care about the falling edge. It's not a necessary mechanism that's used when you're multiplying up a clock or synchronizing a clock within that reference, using that reference clock. So now what we can do is if we do, like, let's say every second we go and we start modulating just one cycle of the 10 megahertz clock, right? So typically that clock is going to be, if you look at the period of the clock, it's about 100 nanoseconds. So if you looked at the duty cycle of 50/50, it's about a 50 nanoseconds high and a 50 nanoseconds low. So what we're doing is we're just going to modulate that one cycle to say, well, let's make it 25% or 25 nanoseconds, right? And then the down or the low of that clock will be 75 nanoseconds. So you're just kind of slightly perturbing the signal, but it's very deterministic because it's always going to happen at the 1 second boundary. And it has no impact to the rising edge of that clock itself. You don't have to manipulate the rising edge. So that's good because that rising edge is very important for frequency distribution, right? Trying to eliminate jitter or noises onto that clock. Anything that's on that rising edge has to be filtered out effectively by a PLL. So by not touching it, you make the distribution much easier. You can use standard buffers and other mechanisms to distribute the clock that they're not even going to be aware that one of those cycles of that 10 million clocks has been modulated or perturbed just slightly within that. It has no clue and it's not going to change the impact of that type of distribution. So I highlighted a lot of this already, right? Why does it remain electrically compatible? Well, like I said, when you do duty cycle modulation, you're not creating any sort of discontinuities into the amplitude, right? The amplitude of that signal doesn't change, right? If it was a CMOS signal at 3.3 volts, it's still going to go up to the 3.3 volts as part of the high duty cycle. And then when it goes low, it's going to go down to the zero duty cycle. It's not going to change. And even if it goes to a differential clock signal, it's not going to have an impact to the slew rate of creating that signal, right? The rise time doesn't change of the signal, and even the fall time doesn't change itself. All you're doing is shortening the duty cycle of how long is it going to remain at that high voltage versus going down to its low voltage marker within that clock signal. So that makes it very easy to distribute, as I highlighted, but it also means the spectral phase details of that clock signal is impacted, is bounded, right? You know exactly how that is. And the energy really doesn't change, right? Especially if you're only modulating one signal. Overall, in that signal distribution, you're not even going to notice it, right? One signal being 25% versus 50 is not going to have an overall impact to the energy that's needed to create that clock. And even shortening that thing doesn't take more energy to do it as well. So it allows you to actually avoid that. It's not going to have any sort of interference with adjacent channel, right? You could have two channels running beside each other and they each could independently modulate their signals and have no impact to each other within that spectral bounds if you're looking at it. So that makes it very useful for distributing that clock or even a multiple clock sources within a clock buffer, that it really wouldn't matter that those signals might be slightly perturbed differently at different cycles and things like that. But for our case, we're not really worried about that because we're going to make sure it's deterministic and put it right at the 1 second boundary. And as I highlighted, this means it's fully interface compatible, right? You don't have to worry about buying special buffers. You don't have to go out and look for an EPPS buffer or something like that. Or you don't have to go and look for a buffer that maybe handles a 5 volt 1 PPS signal coming off a cable, right? And handle that very low frequency pulse and make sure you generate that very high clean edge pulse as a fan out or something like that, right? Almost have to have a very specific buffer just to support the 1 PPS, right? And especially if you're going to drive it over a cable, well, then you need a very specific driver to make sure that that signal is not perturbed going over that coax cable as well, because you don't know the distance it's going to be running, right? So the interface compatibility, we can now use standard CMOS signaling. You can even use differential like HCSL to distribute that clock. Really, it doesn't matter what you use because it's all compatible using EPPS versus a 10 megahertz signal. So now the advantages is as I highlight, you can now go over short copper cables, you can do PCP late traces, it can go over backplane interconnects and all this stuff, especially if you've already created that signal pin to distribute a clock, you don't have to go and say, oh man, I need to add another one for the 1 PPS. There's no need for it right now. You can effectively piggyback off that existing interface without changing the backplane or changing the connector or redefining it, right? So that's the advantage of once you define the interface, it becomes compatible forward and it's also compatible backwards. Even if you want to just only care about 10 megahertz clock, go ahead and send just a 10 megahertz clock. It just won't have the marker, right? But you'd probably just advertise that when that card gets plugged in to say, look, I only send 10 megahertz. I don't send the EPPS. So what's happening? Like how do you do this? How do you actually detect and recover, right? And so, forgive the very rude ASCII figure here. I was planning to do this type of presentation much later, have more time to draw nice figures. But I think from a concept view, hopefully it makes sense. But fundamentally, a lot of the logic that's used, even with traditional silicon that's doing any sort of timing, either clock generation or jitter attenuation or buffers, things like that, the fundamentals are still there, right? You're going to have some sort of input buffer that translates that signal coming in for whatever it is, CMOS, HCSL, whatever it is, it's going to come into the input buffer. And then you're going to maybe look at it saying, well, is it looking at the high edges? Is it looking at the low edges? Right? There's probably some sort of phase detector that's done already, especially if this is going into a traditional like phase lock loop or PLL or even a digital phase lock loop. It needs to basically do its own phase relationship, but it's looking at every edge of that clock. So it's looking at the 10 megahertz clock and looking at the edges. So there might be something that's sampling the edge of the rising edge of the 10 meg and then sampling the edge of the feedback to say, how are we aligned? What's the phase offset? Let's close that into 0 so that I can then synthesize a synchronous clock relationship to that 10 megahertz, but it could be any multiple of that 10 megahertz. It could be integer related, fractional related, whatever it is, and that's going to be my local clock coming out. And then the only really new thing that you're adding, which fundamentally is already in most of today's silicon for DPLLs, is the ability to actually identify that marker. Can I detect a modulated clock that's 25% or 75% modulated and identify it and then make a signal internally to say this represents that 1 pulse per second, right? So here's the marker, use it how you'd want to use it. So how would we use it, right? Well, one, it can be used for phase alignment, right? So in addition to the phase lock loop, which is looking at every edge, when it's synthesizing multiple clock frequencies, especially if it's like integer related or fractional related, right? Unless there's a common multiple between those clock frequencies, it'd be very difficult to find a common edge that all those clocks will come out at the exact same time. Well, the nice thing about 1 hertz is it's pretty much a common multiple to every clock you pretty much generate, right? There's maybe a handful that might be half a hertz or whatever, but fundamentally, most of them are at least 1 hertz multiple because 1 is a common multiple of pretty much every full integer clock you make. And most of the time, we're dealing with clocks that are in the megahertz, and they don't typically have more than 6 decimals of resolution, right? So that's the advantage of this 1 hertz marker is I can now create clocks at 10 meg, 100 meg, 156.25, 2.5 gigahertz, anything I want. And at that 1 hertz marker, I would see a common edge on all those coming out of the device at the exact same time if I was to capture that on the scope. And I could even output that marker to use it as a measurement clock or as a sampler for a scope to say, hey, here's a trigger. If you trigger on this, you'll see all your frequency clocks lined up nicely on this marker. And even there's other ways you can use that marker, right? That we can output it. There's been talks about using the TGPIO, where you can output a digital signal that represent that 1 PPS. You can use it to go out to a connector for measurement. That's how the telecom industry uses it as a measurement marker, so everyone can kind of understand where is your relative error in relationship to the absolute UTC 1 second. I can make a measurement off that looking at the 1 PPS. So that marker could be used as a signal, or it could be used as almost like a reset of the divider to make sure that divider happens at the exact same cycle, no matter what that clock is, a 1 over n or m over n relationship. As long as it has a 1 hertz common multiple, I can make sure it's aligned to that 1 hertz. But even if it's a half a hertz, then you can make a decision of picking an even cycle of 1 second or an odd, right, of that 1 second and still have an alignment relationship, even at a half hertz type interval. So what does this mean that we've now done this? Well, the biggest advantage is anyone that has to deal with 1 pulse per second or a 1 hertz signal knows from a standpoint of trying to use it to actually do something with is very difficult, right? Because all you have is you know exactly where the 1 second interval happens, but what happened? Where's the 256 nanosecond cycle of that signal, right? Or where's the 100 nanosecond of that cycle? Right? Trying to actually splice that into smaller intervals becomes very difficult. So effectively, a lot of people would have to lock to it, try to synthesize a clock that has exactly 10 million cycles or 10 billion cycles of clocks before the next edge, and try to maintain that synchronization only looking at that 1 hertz signal. Well, there's a lot of challenges to that, right? Like you have to have a very low time constant to be able to lock to it and stabilize that clock. And then also, you need a very stable clock to maintain your local clock, because if it's a noisy clock or drifting a lot, it's very difficult to pull back 10 billion cycles to make sure it's 10 billion every 1 second, right? So there's a lot of challenges trying to deal with a 1 hertz signal. And in terms of distribution, it's another hard signal, right? A 1 pulse per second, you only get one sample every second. So you can only get that information every second. Once you've done something with that, you got to wait a full second before you can do another measurement, right? So that's a very disadvantaged concept to do. So wouldn't it be better to have a higher frequency component to actually allow to make that easier? So that's the benefit of now distributing frequency, because frequency is continuous, right? You can use concepts like phase lock loops to continuously track that clock. You don't have to worry about, oh, wait a second, and then let's hope I stabilized long enough in that second to make sure it's exactly at the right time at that edge. I've got now 10 million edges to look at and continuously monitor to make sure that that stability is maintained by the phase lock loop. So that gives you very long-term stability of the clock. You could even lose that 1 pulse marker for a period of time and maintain that marker during that time with just the 10 megahertz clock. So that's the advantage of maintaining that continuous loop, right? And the phase alignment becomes just a discrete event. You know exactly what's going to happen, which means it's very easy to say if it doesn't happen, I'm going to assume that it should have happened so I can do something. Or you could do stuff like corrective actions, right? Did it move? Did it jump? Did something happen? You could do something, right? So that marker makes it a very easy way of saying a discrete event, but you don't have to sit there necessarily and wait, because even that waiting, you've stabilized yourself during that period of time, right? You don't need a big, huge OCXO to stabilize the clock until you figure out what happened to that 1 PPS, right? To say, well, I better just sit here and hope I can stabilize long enough until I figure it out or find another source. The 10 megahertz is allowing you to maintain that. You could almost wait forever, as long as that 10 megahertz is traceable to the same time card constant, or maybe it's traceable to a very good OCXO, but it's only one card has that component. Not each card has to have their own OCXO or a very good TCXO to maintain that constant stability. And like I said, everything else becomes a known behavior, right? So with a slow loop behavior of the frequency, continuous frequency, you're very robust to noise, right? You can do standard techniques of filtering to get rid of high frequency noises like jitter that might be happening to that edge. You can clean it up, resynthesize that clock with very clean edges. And if this is maybe a clock that's being used for distribution, you can even get rid of very low frequency noises too, if you needed to reduce the bandwidth as well, right? So it gives you very means of being very robust to any sort of noise that might be occurring on that clock. And that marker is preventing any sort of long-term drift, right? So even if you wanted to independently maintain your own clock source, right, you could still use that marker as a very stable indicator to say, how far am I drifting with my own clock recovery algorithm that I'm using? Because maybe you're recovering a clock that is not traceable to the absolute UTC time, but maybe it's traceable to some other component, and you just want to make sure that you're not drifting over time and maintaining a stable clock recovery of that component. So that marker gives you a lot of benefit as well. And then the system effect is very, much the big thing, right? You've now eliminated any means of having any sort of phase accumulation ambiguity, because you know exactly how that phase is occurring. You don't have to sit there and wait to do a reaction. You don't have to do predictive algorithms. You don't have to do your own adaptive clock recovery algorithms to try to recover a clock with only maybe a 1 second marker, or with maybe only like 16 packets per second information coming from PTP, right? You now have the ability to maintain that over a long period of time with the 10 megahertz clock. And of course, this all brings down to is you can now create much more robustness into your own designs, right? You can now create fundamental concepts like redundancy, right? I could put 2 time cards into a system and each send out an EPPS, and now I have redundancy, right? If one fails, people can switch over to the other, right? If I want to do monitoring, I can compare the two time cards in relationship to each other if they're coming from different sources. One's maybe coming from GNSS, the others may be coming from PTP over the network. I can now do some monitoring and things like that. So you have all these things that you can take advantage of because of the physical clock, as opposed to relying on a 1 hertz signal only to maybe only detect what happened a second ago, right? It's always going to be like what happened as opposed what is happening. That's the advantage of the multi edges that you get with the 10 megahertz. And as I talked about, there's a lot of mitigation controls you can do now. You can do filtering through bandwidth control. You can detect hysteresis, like maybe that pulse per signal jumped from one cycle to the other cycle, which is like a 100 nanosecond jump. You can kind of sit there and say, well, is that real, or is it whoever's embedding that maybe just messed up and got it on the wrong cycle and it comes back, right? So you can put hysteresis detection because you still have the 10 megahertz clock to say it's very difficult to steal cycles away from a clock, right? And it's very difficult to go something like backwards in time on a clock as well, right? So even if it did maybe shift backwards a cycle, right? You don't have to actually say, well, let's just eliminate the cycle and do 9.999999 million cycles this second, instead of maybe just mitigating that by saying, well, a phase lock loop could slowly transition to that alignment through some sort of frequency control, right? So it's a smooth transition. So you can't have concepts like going backwards in time, which are going to be hugely devastating to something that's trying to capture events, and you have to worry about relative error time events of when those events occurred. Especially if the own system goes back in times and sends an event out that looks like it happened earlier than an event that happened within the same system just because you went backwards in time. You don't want that. So you want to be able to mitigate that cleanly through PLL smoothing techniques and to do its own phase corrections, which means you won't go backwards in time. It may just temporarily speed up or slow down to mitigate that change that may be detected because maybe there was a failover. You went over to another time source. It slightly is off a bit different from where it was from the other time source. So you want to try to transition and track it within using more PLL tech capabilities than trying to manage it through counters or subtraction or addition and make sure you don't do something like go backwards in time and things like that, or even repeat time, right? Repeat the same time in 2 cycles would be very bad for PTP because then it looks like they happened at the same time when they really didn't, right? Physically, they did not happen at the same time. So you don't want to create that condition just because of your mitigation techniques of handling a movement of where you think that 1 pulse per second is really in your system. So what's the PCI SIG trying to do for this, right? So this is talking about like now, okay, great. We now understand EPPS. Hopefully now you're seeing some of the benefits of it. But you know what? I don't want to have a proprietary way of finding it, right? Like I don't want to go and have to say only vendor A gives me this capability, vendor B does it, but they do it a little bit different, right? How do we make it so that it becomes more open, common, and easier to get access to this? So what we want to do is that's where you have to rely a bit on standards, right? Have the standards kind of make the big decisions of, all right, I'll give you an ability to do clock distribution. We'll reuse certain signals. They will be common for anyone that is compliant to PCI Chem 7 or higher. There'll be compatibility forward and all that stuff. And there'll be how do you negotiate what capabilities do you have when you plug in that card and things like that, or remove the card and plug in a new card. There's some sort of handshaking and all that, which makes it scalable. And also, to replace cards, it makes it much easier. You don't have to care who the vendor is and things like that. You just know that they all follow a common technique. And so the PCI Chem 7 is trying to do that with they've actually added a new section called time synchronization enhancements, right? They just said, look, let's take the same ideas that was happening at the OCP NIC. Let's take the standard PCIe SIG compliant card connector that we use today. Let's look at some pins that maybe aren't really used today much, like the JTAG pins, which very few people are doing JTAG scanning anymore within the system. Let's reuse a couple of those pins and let's define them as EPPS in and EPPS out, right? So they only took 2 pins, right? So very efficient, right? They just said, look, I don't need 6 pins, right? I'm just going to take 2, one going out of the card, one coming in the card, right? So you create the ability to do clock distribution. You create the ability of putting timing into cards, like the time card could be a plug-in card now. It could be coming off a NIC that supports synchronous Ethernet or PTP coming in, or even White Rabbit, getting that clock in, and then it's basically pushing that clock into the system, right? And you can create redundancies, right? You can create that something in the system could sit there and take, well, if there's more than one EPPS source coming in, I'll only use one for the distribution, but if there's a failure or if the card's pulled, I can fall back to the other, right? So now you can build the redundancy into the cards as opposed to into the server itself, right? So there you get a cost advantage as well. You don't have to put OCXOs directly on the server or get customized server cards that have these OCXOs sitting on it to give you the stability of the clock if nobody's plugging any of these time cards in. You can now just buy it off the shelf, plug it in, and get the time card capability up front. So, and this extends the lifespan, right? Now, like I said, it's now plug and play, right? You now can add time cards, remove time cards, replace time cards, next generation NICs, acceleration farms, whatever you want to do, accelerator cards, GPU farms, anything can be plugged in and take advantage of this EPPS clock to create some sort of clock distribution and synchronization in order to improve that, right? So it's something that just didn't exist and it's going to exist from Chem 7 on going forward. So it extends that lifetime of that connector card. It's going to be very flexible for any changes that may happen, right? Those clocks might get better, might get more precise, might do whatever. It doesn't change how it's distributed in the system because it's represented by the 10 megahertz clock and the 1 PPS marker. And like I said, it's already happening, right? We're starting to see it already in some of the concepts, right? Like you could take now these time NIC or tap cards that are some people are manufacturing, and instead of using that coax cable screw in at the top of the card to maybe put it off to another card, they can now actually put that EPPS over the connector. And most of these cards already are using PLLs that have that capability of embedding it. So it's just basically routing that signal to the connector pin and turning it on, right? And we can start getting it going. So, it can be built upon already today. And there's already cards coming out that support that EPPS coming in as well, right? That can take it in. Right now they might be just bringing it into a buffer to distribute it, and they just treat it as a 10 megahertz clock. Or they may send it to some sort of smart synchronization device that can decode the 1 PPS and output the 1 PPS to ASICs that maybe don't support the EPPS directly into it. But we're even seeing some ASICs themselves starting to support the EPPS or FPGAs because, like I said, the concept isn't difficult and it's open. Nobody has a proprietary mechanism of how to decode a modulated clock, right? It's very difficult to patent that or something like that, right? So it's a very open concept. So it's very easy especially for FPGAs, but even a lot of ASICs to start decoding that signal off or that marker off of that 10 megahertz clock. And 10 megahertz really isn't a fast signal, right? Like you have 100 nanoseconds in between cycles, right? So you really only have to splice that up into like maybe 10 nanosecond chunks. Well, most analog circuitry today can go well beyond that. So that is not a difficult thing, right? Most circuitry now, we talk about picoseconds of accuracies of measurement, right? So doing it into tens is fairly easy, and most off-the-shelf components probably can do it. But like I said, most even silicon phase lock loop technologies today have an integrated mechanism to measure clocks and even do, convert that even to a digital representation of what's the phase difference if you want to do measurements. But it can also detect, right? It doesn't have to only look at rising edges. It can look at falling edges and tell you when did that occur, right? To aid in your own marker detection within it. When you see one cycle goes from 50 nanoseconds to 25 nanoseconds, that's a marker, and you can detect it using these time to digital converter techniques. So, again, apologize for the crude drawing, but I tried to demonstrate, well, what does this mean, right? Like sometimes you just have to physically see it, right? Like, is there really a problem, distributing 10 megahertz and a 1 PPS and using cables versus traces? Well, that's hopefully what you're kind of seeing on the left side, right? If you take the traditional path of like, okay, let's say we just take the 10 megahertz clock and create a one pin to distribute that clock over it, goes over traditional fan outs like we talked about, so no issues there. These are off the shelf components. And that 10 megahertz will eventually end up at a phase lock loop or maybe directly to the GPU, CPU, and they can use that clock. But then if the time card is sending the 1 PPS, it may have to fan it out because it has to send that clock to maybe 5 cards. Well, that means you have to split the signal into 5 copies, right? And then you got to screw on all 5 of those cables to each one. That means they're different lengths, right? There could be bends, there could be things that could affect the signal that attenuates it. All this stuff can start having impact, or they didn't screw on the connector tight enough. Jason Rock highlighted some of that where he found that was one issue where just found out it wasn't screwed in tight enough, right? So it just wasn't making the connection. And he was wondering why he couldn't detect the 1 PPS or why it was very attenuated when they were trying to look at that signal as it was recovered, right? So these are the things that you get with cables, right? When you look at connectors and traces and all that, a lot of that stuff is better confined, right? It's a harder, your connector pins are all within the same length because the chem spec defines that they have to be the same length, right? So you know exactly what sort of characteristics you're getting over the connector. Most traces are known, or you can define worst case traces of how long they're going to be, right? And if you want to eliminate that, you can use fan out buffers. They even have zero delay fan out buffers where they try to make sure that the phase relationship as that fans out is maintained. So that's like zero propagation delay as reconstructing that clock, right? There's a lot of these things you can take advantage of. But as soon as you throw a cable in, you really lose some of that, right? So now when you look at the two paths, you have to look at what's the phase error between that. And that error could be larger than the 10 megahertz signal, right? It could be greater than 100 nanoseconds. But what if you actually multiplied that clock up before it got to the GPU, right? Maybe it's a 125 or a gigahertz clock coming in. Well, then now it could be multi-cycles error off when you actually get that 1 PPS. So it's not just finding the nearest edge. You don't even know which edge of that clock does that 1 PPS really belong to because the overall phase error has accumulated because it went down a different path. So what does EPPS give us? It gives us a single path distribution, right? So now you get very deterministic alignment. It means you can use very deterministic and off-the-shelf components. So those zero delay buffers work just the same, right? The fanning it out is just the same. The traces you have control over, right? I can make sure the traces are bounded within a certain length, plus minus error, right? And so that every card effectively gets that signal at a well-defined deterministic alignment component, right? And you can then take that and decode it and recover it any way you want at the end source and know that all of them are almost seeing that 1 PPS at the exact same time in relationship to each other, right? So it makes it so that now this inter-card distribution, you don't have to rely on outside out of band techniques to try to synchronize their clocks, right? If this is a bus communicating between cards, you don't have to do something fancy to try to say, well, let's make sure we're kind of talking on the same page. With this, you now have this marker that can tell you this is when we'll start talking, right? Or at least we know at this point in time, we should be at this cycle of the clock. But there's a lot of other things we can now do with this, right? Like once you've created this deterministic timing, there's a lot of things. So all the stuff we highlighted at the beginning, hopefully we all remembered, is we now can do stuff like look at, well, how can we manage AI workloads, right? How can we eliminate this barrier of, well, there's this alignment between GPUs, right? I may have a server that has multiple cards plugged in, right? And I don't want to now worry about how do I keep those all nicely aligned. I can now use EPPS to say, here's a marker, keep it aligned, right? And it doesn't necessarily mean you have to create the bus's clock off that 10 megahertz, but that marker is going to be very stable and its known relationship to the other cards is going to be known. So that marker could be used for whatever purposes it needed. It may not even be 1 PPS. You may even just create a 10K or another frequency that's a little bit higher to say, use it for like scheduling, right? And say, well, let's have a guaranteed scheduling slice that occurs at a known time. Or I could create relative scheduling between GPUs by saying, hey, you're going to use this cycle of the 100K clock, you're going to use this cycle, and start staggering scheduling and stuff like that, right? So there's a lot of stuff you can do with that marker. And then, of course, for networking, it can be used for a lot of the stuff we talk about, like congestion control, round trip delay, all these things, because you know that you can even do this over networks that maybe have common time sources, traceability, like to UTC. Now you can use that 1 PPS to give that stability onto your NICs or anything else that's looking at how to manage some of that control. And of course, it gives you very easy observability to anything that's happening with the system, right? You can now do tracing, you can do synchronous telemetry. There's a lot of things you can do, and you truly can start offloading maybe tasks that weren't historically in the cloud, like telecom. You hear about AI radio access networks, right? Now you can actually participate with the synchronization that's happening within the radio access network and things like that. And you can see that observability and even act as a telecom node itself, because you can get that precision of that clock distribution that you know you can maintain very little error going from even one NIC card, like the time card, to another NIC card that's maybe dedicated to do the distribution unit concept of the radio access network, right? And there's even new ideas that are being talked about, right? Even the PCIe SIG forum for the PCIe clocks is talking about, you know what? Instead of maybe looking at always having to rely on common clock, and where even independent clocking, where the spread could be happening independent from each other, you could use this to actually get coordinated spread spectrum clocking within this. So this will help with deterministic behavior. You still get the benefit of the spread spectrum for EMI considerations and stuff like that. But now you could coordinate some of that so that maybe instead of worrying about when does a spread start at one side of the bus versus the other, you know they're coordinated to start at the same time. So it makes it easier in a lot of that even data recovery at the other end. And so there's things like that that's starting to be looked at when they start saying, hey, there's a way we can coordinate things using this deterministic marker. So let's summarize. Hopefully I have a little bit of time for Q&A after, but what are some benefits, right? So hopefully these are the things you got out of this, right? We're trying to find a way to simplify some of the system integration, right? Let's get away from proprietary means, or let's even get away with cables, right? Which are a very inefficient way of trying to distribute any sort of signal, be it a clock or a marker, not an efficient way, right? Let's look at ways we can enhance the scalability, right? How can we just do this as almost as easy as plug in a card and go, right? And get access to this very precise clock, and even if needed, a very deterministic precise marker that indicates where the 1 pulse per second behaves. And then everything else out of band becomes trivial, right? If you need to know the absolute time of day based off that marker, well, it's very easy to send seconds in a 1 second interval, right? To be able to tell something, here's your second interval, and the 1 PPS is just making sure that the rollover point happens at that precise point, right? So now you can distribute these counters anywhere and recreate precision timestamping without having to distribute precision clocks, right? You don't have to say, oh, how do I do white rabbit within my system? How do I do this? You can get it with this type of thing, right? And reconstruct the same precision. So you can still get these sub-nanosecond alignment improvements that are all being touted over these network distribution capabilities. But there's always the challenge of how to take advantage of that when your own system is in the milliseconds of accuracy, right? How do we take advantage of sub-nanoseconds if we can't even distribute it within the milliseconds, or even tens or hundreds of nanoseconds, right? There's no advantage of the sub-nanosecond clock coming in. And we get to take advantage of some of the open platform leadership, right? OCP is on board with it already with the OCP NIC. PCI SIG is now on board with standardizing it. Yes, maybe they're a little slower than some of the OCP projects that are happening that can maybe get things going quicker. But like I said, the adoption of this is already happening. So you don't have to wait. I just want to make it aware that, hey, it's coming. It will be a standard. The PCI SIG is trying to improve their timeframes to get faster releases of their specifications because they know some of this stuff is happening quicker than they are able to keep up with. But it doesn't mean that you can't go off and say, hey, I can still talk about this with my vendors, right? Why I can go to vendor and say, hey, do you support EPPS, right? Or, hey, server card, I hope you're putting EPPS support into the next server so I can distribute this clock and take advantage of this, right? And things like that. So hopefully these are things that are going to raise a lot of questions for you to go back to your teams and I'll go for this. And it's also people that are involved in other standard bodies like the P3335 for the time card, right? They're talking about how do we distribute clocks off around, right? Is it over the PCI bus? Is it using PTM? Well, here's now another means of doing that, right? Using the 10 megahertz with the embedded pulse per second. The other things here, I'm going to just slide over. These are more just verbal captures of what I've already talked about. So don't think I'm skipping over anything. I guess to me, the big takeaway is probably this one, right? Which is the big thing, right? The big advantage of OCP is we want to look at ways of improving the scalability of the architecture, right? How can we work across different systems that are being put out there? The NIC, the GPU, the CPU, right? How can we create a compatible interface that allows everyone to take advantage of this? And so I think this is the thing. You don't have to sit here and say, well, is it SyncE? Is it P2P? Is it GNSS? How it gets into the time card isn't the important thing. Because honestly, if you don't know how to distribute it, it doesn't matter how good you bring it in. You have to have access to it, right? So let's create this mechanism to get access to it very precise, right? There's no way you'll find that the PTM without huge enhancements can get to these levels of accuracies. Or PTM may rely on this to stabilize the frequency component, right? And use it for that. So hopefully that's some of the takeaways you can take. And like I said, just as a conclusion, if you're not involved, definitely get access to the Chem 7 draft that started talking about this. The more contributions and push into this, the faster it'll get into words so that we can start building cards on this and demand this flexibility, the scalability up front. Don't rely on anyone that says, here's a cable to screw in to get 1 PPS, or hey, here, buy this expensive technology to get White Rabbit into the NIC, and then you're like, and then what? Right? And then you hear crickets, right? So now you can build off that to say, okay, if I'm going to invest in getting very precise time in, I want to be able to get access to that throughout my system, throughout the rack for this type of thing. And with that, I will wrap up. Thank you very much. And hopefully that wasn't too much rambling.
Oh, thank you very much, Greg. This was great. Like so many questions. I think I have. I mean, to start with, like perhaps we need also to standardize somehow what goes on the motherboard when you have like so many, let's say, possibilities, like some sort of a clock matrix or something. But before we're getting into that, I was wondering, was there a study done on the whole space of like this combination of the 1 PPS and then 10 megahertz and like let's say have all those possibilities and then the possibilities were checked in terms of let's say advantages and disadvantages and so on. Was there something this done? I mean, it's very interesting to revisit it because I mean, for example, I was just looking at it and I'm like, okay, if I need to implement this on the FPGA, let's say for the receiving, I have to take account to basically timestamp every time I get a rising edge, then watch for the duty cycle, see if the duty cycle is normal, discard. If it's not, keep. While I could have had like the standard slightly tweaked where the duty cycle before, the rising edge coming is anomaly and then I basically open the gate, wait for the pulse per second. At that point, I can take my timestamp and go for it. But then, as I was thinking further, I was like, well, generating is going to be now a problem because Like if it was just send this pulse and make the anomaly, now I have to know ahead that like, oh, tweak this because I'm gonna send it next. So I mean, it just
Yes.
goes like back and forth. And I was like thinking like if this was already studied before, I mean, you can also look at like, oh, give a quadratic thing, like basically change by 90 degrees something. I mean, I don't know. That's kind of bad because it makes problem with the spectral thing. And I'm like, is there a study done like on all of these? It's pretty cool. I wanted to. I'm more for my curiosity and I want to learn this. It's like how you guys concluded this. I think it's a very cool thing to like have a reference if it's already done for the community.
Yeah, for sure. Very good questions. And yeah, I agree. Like there is a lot of history, right? There's a lot of history, probably predominantly in the telecom because the telecom is was probably the first time where the drive of having to get more efficient means of distribution
Yes.
was started coming up, right? Because they already had a long-term fundamental infrastructure for what they called frequency synchronization or for network synchronization, but it was predominantly based off a frequency of the clock, right? They only cared about the relationship in like, PPB relationship to that clock.
Yes.
But then when 1588 came around and they started needing to get access to this marker, the problem, especially with Ethernet networks, is a lot of the stuff that they used to be able to kind of take advantage of in the old SONET SDH is the protocols themselves were synchronous, right? So
Yes.
this marker was already built into their own signaling, right? So I think that's where some of these concepts started coming about, saying, well, why can't it just be just a simple marker? It doesn't have to come 8,000 times a second, right? If you have another clock to use to try to help that. So this is where some of that started happening is they said, I don't need to send a separate signal for 1 PPS or even 8 kilohertz and then send the clock itself, right? And so they're saying, how do I make that more efficient? Now, a lot of times that didn't matter because they already had counted for multiple signals of the clock, right? Every card in a lot of these telecom systems already was getting a clock and the sync or a frame pulse, they called it, right? So they didn't care. But it wasn't until 1588 came that they realized, unless we go and redesign all our architecture backplanes, right, we got to find a way to reuse some of this, right? And so this modulation technique started becoming popular, right? Saying, hey, it's a simple way of just getting very simple indication of a marker. But
Yeah.
you highlighted a good point. Like yes, from a visual perspective, seeing that marker occur exactly at the 1 hertz boundary is nice, right? Because it's very visual. You know exactly where the 1 second is.
Yeah.
But from a perspective of usage, it does make it a little bit more challenging, right? Because like you said, it becomes a reactive nature, right? You see
Yes.
the marker, then you have to almost be reactive to say, well, I'm going to assume the marker will come here again. So you make the assumption it's going to happen. So that's what you treat your system level as. And then it becomes more of a check, right? Because it
Yeah. It
says,
becomes a
okay, did it
keyword.
modulate? Yes. Okay, I'm right, right? Because you know the carrier of the frequency component is exactly in the same synchronization domain, right? So you know it's exactly 10 million cycles. So you can effectively count it. We don't count it, but you can effectively count it to say, I know it's going to occur at this
Yeah.
time frame.
Yeah.
So I think that's why the leaving it right at the marker, right at the 1 PPS, just kind of stayed, right? Because they realized the reality is most timing silicon has already built into the idea of it may be, actually finding out when did it occur is always going to be late, much like determining when did an event occur. It's always in the past, right? Like you never know what time it is. You know what time it was, right? So
Yeah.
so it's the same idea. Is you have to almost just say, well, I know what time it was. I'm going to try to predict exactly where it would be next and confirm it. So it becomes more of a confirmation. That's why, to me, using the term of a marker is almost better, right? You
Yeah.
just want to say, is the marker still consistently occurring where it's occurring? Because the 10 megahertz clock is becoming your fundamental factor, right? You
Yeah.
don't need to keep track of counters. You could count edges of the 10 megahertz if you wanted to, but there's systems now that can lock to it, multiply it up. They may even have their own integrated counters. A lot of things have counters like a time of day counter you can go read. You can even use like snapshotting of when an event occurred, send a signal to a device and it snapshots when it happens because
Yeah.
it's using its own internal clocks that are running at much higher rates
Yeah.
than the 10 megahertz, right? So you can get more precise measurements, right?
Yeah.
Which is why we talk about picoseconds of measurements when we do a lot of our measurements, because we have the ability to kind of slice that up
Yeah.
internally, right?
Yeah.
So I agree. I would say there was any big decision on should it be on the marker before or after. I think the reason, like I said, the reason, much like everything, is once someone's proven that something works, they just kept it, right?
Yeah.
So
There's inertia then. Yeah.
exactly. So no one failed saying, well, I can absolutely not recover the 1 PPS if it's not on the cycle before. They just said, well, let's just make it on the cycle of,
Yeah.
right? But I agree.
Also,
But and honestly, it doesn't prevent us from defining that, right? Like in going forward, if someone defines the interface, even a card plugged in could say, hey, I put the EPPS out, but I do it one cycle before, right?
yeah.
Or maybe it's programmable, right? And you
Yeah.
can
Yeah.
say, when do I want it, right?
Yeah.
That doesn't change the interface, right? It doesn't change the fundamentals of the
That's
EPPS.
right. That's right.
Yeah.
So one more thing is this basically rides on a 10 megahertz. So you will have like 100 nanosecond of resolution. If you want to do it like for high resolution, you have to basically also recreate the clock.
Yeah.
You have an oscillator and you regenerate now with tighter phase. Is that correct?
Correct.
Yeah. Okay.
Correct.
And
Yeah,
and
so this is where you can use like traditional phase lock loops, right? Most phase lock
exactly.
loops today lock to a low frequency clock like 10 megahertz or something like that and regenerate any clock, but it's
Yeah.
all phase aligned. And that phase accuracy is like sub picoseconds, right? Like, when we talk about phase noise error of a clock, when we resynthesize and generate a clock, we're talking femtoseconds now, right?
That's right.
In that. So you can't beat those type of accuracies with the physical synthesis of the
Yeah.
clock itself. Yeah.
Yeah. And then the Chem 7, does it define also what should sit on the motherboard, the clock matrix or something, or that
Yeah,
one is
I would
open?
say today, no. I think what their focus really is now is just on the connector itself, like
I
making
see.
sure that pins is defined and
Okay.
making sure that the record to be able to query information between the cards when they're plugged in, they're kind of working more on that. I
Yeah.
think probably, honestly, I would probably say something like trying to understand what would go on the motherboard. To me, that
Yeah.
would be probably a good OCP initiative, right? Like we
That's
have it
right.
at the NIC. The OCP NIC already kind of did it, right?
Yeah. Yeah.
Maybe we can find something where we can do something with the OCP
Yeah.
motherboards and say, hey, let's come up with a way of doing clock distribution. And this might be the great platform for that, right?
I
With
was I
the
was actually
laptop.
also thinking I mean nothing bounds us to this. We can take the 100 megahertz that comes back like via the root complex, I mean via the motherboard to all the PCA devices, have EPPS in that one, and then all the devices they basically recover the clock and the phase of what the motherboard has, and then they can either use it. I mean, there's something here, or like basically they compare it to what they have, and then all of that is available in software. Let's say, for example, it's kind of like leans toward like what Julian did with something similar. So basically now, but you recover also the phase now with it, and now
Yeah.
you use numerically for the one that is source. You basically just read from, and for the one that are following, now they take that and regenerate for their needs. And then by that you kind of have it soft and everyone is just listening so nothing can break. And I mean I really want to, regardless, I mean I want to have this implemented on the time card. I'm assuming I just route those two pins to the FPGA and then leave it for creativity.
Yeah, pretty much. That's what I'm pushing for, right? Let's make it simple. Just route them like clocks and hook them up, and the support's going to come. Like the
Exactly.
FPGAs can support it already today. Like I
Yeah.
said, we've done it with vendors, so it can be done today. You can use off-the-shelf silicon,
Yeah.
to get it for timing. And then Intel's done a lot of stuff with trying to abstract this. So even the concepts like a DPLL, they've already started to abstract it within the Linux layers with the
Yeah.
DPLL subsystem. You already have the PHC, for the PTB hardware clock, but to me now it should be called the precision hardware clock, right? The ability to be able to do anything to do with precision the
Well, I
precision
think
hardware clock.
somewhere I heard like physical hardware clock. That I mean, yeah, but precision.
Exactly. So we all it's going to create is we need something that talks about this physical clock, right?
Exactly.
And but that's going to come, right? Like I think that's what we can build off, and it becomes scalable, right? It just becomes a plug-in component once the motherboards support it.
Yeah.
It becomes more of a plug-in component, right? You plug it in, and then the precision you need is determined by the card you plug in, right? You plug in a time card that does just has no CXO, well,
Yeah.
that's what you get. If it
Yeah,
has the
I'm
full
glad. I'm
DNSS,
glad the Nick 3.0 actually came to fruition. Like I had a hard time pushing that through. And I don't know if you want to know if I mean for the others, perhaps the background story was there was not enough room on the Nick 3.0, I mean on the OCP form factor Nick for the PPS in and out. So we
yeah,
had to basically have them on the board. And then there was also the lack of devices. Like I mean there were one or two vendors that they had PTM and the rest didn't. And we were like, how can we push the time like from PTP precisely into the system with PTM? And again, PTM was not even that far. So that's why we took those pins. We were like, how about 68? I think 68 and 69 or 69 and 7. I think 68, 69.
yeah, something
And
like
then
that. Yeah.
yeah, the easiest we're able to push without causing problem with backward compatibility and like don't break things, evolve things, and so on was like this flex IO. And then because I mean, when we did it, they were like, "How about 10 megahertz?" I was just asking for PPS, you know. And you're like, "Why 10 megahertz?" And then the telecom guys like, "We need 10 megahertz." So I was like,
Yeah.
"Ah." Then put both, and like, how about input output? They're like, one input, one output. You can choose PPS in, PPS out, and that was the reason why we called it flex, you know. And then EPPS came and just solved everything, you know. That was awesome. Anyways, let's open the floor for more questions.
Yes, for sure.
Pervis.
Sure. Hey, Greg. So I think Ahmad touched on this a little bit. So the typical EPSS distribution is basically to a single CPU GPU complex, right? So how do you handle multi-card topologies? Is it more of a server-side problem, or is there something else that can be standardized around that side?
Uh, I think I guess, yeah, it becomes a server kind of problem, but it depends, right? Like the simplicity of the EPPS, it could be really just used where, EPPS comes into a mux buffer on the server card, and then it just distributes that clock to every other card connector as the EPPS in, right? And if you do that, you just kind of say use it as you want it. It's just a fan out
Hmm.
clock distribution, right? It's simplified. But if you want to start saying, well, what if I want redundancies and resiliencies and stuff like that, or and maybe some server cards will do better calibration out of some of those delays, right? They might say,
Hmm.
hey, I will guarantee the max propagation delay of that clock signal will be X going to your connector, right? And then
Hmm.
the card plugged in can then say, well, from the connector to the CPU, GPU, I can manage that as well, right? So it starts becoming more of the card and the server. There'll be some, the aspects of that is going to have to be taken on by those groups. So that's where I said I don't think the PCI SIG is going to run with that, in my opinion. Just because it'd probably be difficult for them, right? It's just like they don't really define exactly how PCIe clock tree has to be, right? They just basically
Yeah.
say it's going to come over the connector, and these are the characteristics of it, right? Is it Gen 1, Gen 2, Gen 8, whatever it is? That's all they define. So that could be just all it gets defined is there might be different classes of the EPPS of saying this is EPPS class A, it has this characteristic coming off the server, right? And then there might be a B in the future, right? That has
Right.
more precision, right? So I think that stuff is going to evolve, right? But I don't think we would sit here, hopefully, and rely too much on probably PCI SIG. I don't think we're going to get that. Maybe they'll jump on board and define it similar to their PCIe clocking and that, but with PCIe bus, right, it's a bigger thing, right? So I think
Right.
that's why the SIG group is really focused on it. I don't know if we're going to get that type of traction to support EPPS, right?
But is there already an interface or enough pins to handle this exchange of capability exchange,
I would
as
say
in?
yes, it's already there. Like just creating the in and out of EPPS to each connector card of the PCIe
Hmm.
connector card itself. you've created effectively what historically has been used in telecom, right?
Yeah.
So in telecom, for complex chassis-based systems, they have concepts of what they call line cards,
Right.
right? And the line cards will take in recovered clocking and then send a signal up, right? And then they have a concept that there's this time card that will take this and then distribute the clock back down, right?
Yeah. That
So
goes
that
back all the way to the old bits interfaces and the SDH
exactly,
clocks and everything.
exactly.
So yeah.
So all that capability is now built in, right?
Right.
So now the support of it's there, but defining the time card is coming, right? So the
Right.
time card is coming, which the time card may push the concept of saying who is managing the EPPS, right? Who is actually going to handle concepts of what if there's more than one time card plugged into the system and there has to be some sort of redundancy or resiliency function
Right.
put in, where does that belong? And that's where I
Yeah.
see someone saying, well, that makes sense to be on the server board, motherboard.
Right.
And then we start saying that's the block, right? But I think that's going to come over time. Honestly, I think for the first phase of it, it's just going to be simple clock distribution, right?
Sure.
Like it's just going to be, if you plug in two time cards, those two EPPSs will be routed to some sort of selector mux that can select
Sure.
one or the other, and then it distributes that clock over connectors to all the connectors. If there's a failure, it's just literally going to be a crossover, right?
Right.
And then that's where you might get this jump in one PPS because one time card may not be perfectly aligned with the other. So you have to say, how do I mitigate that jump, right? But that comes into the card, the line card.
Yeah, it's more could be simple arbitration initially and then could be more
Exactly. And then in a way
complex.
that becomes the arbitration for the application, right?
Yeah,
The application can choose what they want to do.
true.
They can ignore the new marker, they can transition to the new marker, and they may not even be using the markers. They may, like Ahmad said, they might just be looking at it to help coordinate their own
Right.
synchronization or timing, right? So
Got
we
it.
don't. The idea is you want to abstract the end application, very similar to how telecom typically did it. Is just say, look, we'll figure out a way to get the clock to you,
Hmm.
and over time there might be different classes of what those clocks are, and then you can use them as you need, and there's a way of communicating what class am I, what
Got
is
it.
the server giving you, right? Is it giving you redundancy? Oh, okay, thank you, right? Is it giving me mitigated switchover? Oh, okay, communicate that,
True.
right? So over time that's going to come, in my
Okay.
opinion, but you're not going to get it overnight. That's,
Sounds good.
yeah.
Thanks.
No, thank you.
See,
All
one
right.
more quick follow-up before I jump in, Ahmad. Sorry, quick one.
Yeah, go
So
ahead.
you mentioned 10 megahertz primarily because of the telecom, legacy, inputs.
Yeah.
But are you concerned at other frequencies that you are going to have minimum pulse width considerations with respect to, edge detection, rise detection, and so on?
Yeah, there's definitely from a standpoint you want to limit it to certain frequencies. I've seen this demonstrated all the way up to 156.25. If you really had to, if you're just modulating one signal, it's not that difficult. It's the modulation isn't the hard part because, like I said, most circuitry today is generating the clocks by effectively creating a duty cycle of that to get that frequency. So, the splicing of that is already inherently there. So if you can
Yeah,
generate 1 gigahertz, you're already creating a 1 nanosecond
true.
period, which means you're already at a half a nanosecond, 50% duty cycle. The problem is when you say that 25%, it's the detection, right?
Yeah,
You're
that's what,
getting
because the
hard to
edge
detect
detection
this, right?
requires some minimum pulse width, right, for the
Exactly. So then
PLL.
you have to
So,
argue, well, what's the benefit, right?
yeah,
And that's the thing is historically what we found is 10 megahertz is really kind of your optimum frequency, right? It's a nice even
true.
for the period, 100 nanoseconds, right? Nice. And it's fast enough that
And then you can,
it allows you to maintain the phase lock and
true.
very good traceability to it. And it's also slow enough, that it's very easy to read it or splice it to be able to determine anything to do with the duty cycle, right?
Got it.
So in a way, I think that's why 10 megahertz became popular. But yeah, we've seen 25 megahertz used,
Hmm.
especially in some backplane applications. And honestly, it may even be, maybe there'll be a switch to go to 25 meg because it's probably a more common clock frequency used in cloud servers, or it may even go to 100 megahertz. So, and as the mod highlighted, why not? Why not start modulating the PCIe 100 megahertz clock itself, right? And start using
Yeah.
it. And we dabbled with that a few years back. But the big thing with that one is you get some pushback because sometimes that 100 megahertz is actually used directly as the clock. So manipulating the duty cycle is not good.
Yes.
The other issue you got was with spread spectrum clock is what cycle do you modulate, especially if it's already being modulated because of spread. You're already moving the frequency component of it. How do you actually lock to a spread spectrum clock to be able to do this slicing, decoding, and keep this synchronization? It adds a little bit more complexities, which is why I think they're looking at maybe more of a coordinated spread spectrum clock. It makes it a little bit easier because then you could distribute just 100 megahertz and then coordinate the spread at each card.
I see.
And do that. So
sounds good. Great. Thanks.
Yep.
All right. Any more questions?
Have you considered automatically determining the delay in the cable?
There's definitely ways you can measure delays of cables. I agree. There's techniques you can do. The GNS systems are starting to do it now already, right? You can do stuff like round trip delay measurements, which means you can then compensate out delays of the cable. So, I think there's techniques. To me, the biggest challenge of the cabling is it's not scalable. It's not a simple way of doing it internally. Very difficult because you got to pop open the system every time you add in a card, right? So not very scalable, right? And these days, it's very rare that you plug in a server card as is and leave it for 10 years and not touch it, right? Like you're replacing cards, you're doing stuff. So having cabling is not efficient. And then, as highlighted by Jason Rock in his presentation a couple months back, even just going even card to card, even if you try to do it externally to say, well, that's how I'll make it scalable is I'll do it externally. That's what they're trying to do. And he's like, it's so difficult, hard to get your fingers in there. So that means you're hiring people with small hands, to do all your stuff. So I don't think it's going to be something that's just your long term. It's just not a long term scalable solution to go to cabling. It's not about that you can't calibrate out the delays. I think it's just much of those techniques can be the same techniques you could use to calibrate out connector propagation delays, even buffer delays, or even trace delays, right? Like, and it's all stuff that's already been done in telecom to get sub-nanosecond clock distributions within the system, right? They're doing all this techniques already. So EPPS is just building off that. You can create round trip delay sampling of those markers to measure delay if those traces are the same distance or length between the two systems talking to each other, right? So you can do round trip delay compensation out just right there as well.
Just building a little TDMR or something. You also were talking about putting this onto the motherboard. Have you looked at TGPIO?
I would say I'd say yes and no. Definitely. I think there's a lot of places that it can go. Right, I agree.
Okay.
I think again, this is something where I don't think it's going to be. We don't want to sit and wait for PCI SIG to define stuff like that. I honestly think this is a very prime candidate for something to happen within the OCP, and specifically since we have the time appliance project, it might be a good thing to do here, right? Let's come up with some of these ideas, and we could submit them to whatever OCP organizations that maybe run with it. Like there's ones that will look at OCP motherboards, just like there was for OCP NIC. And like Ahmad said, you just push them to say, hey, let's go this route, right? And the more you show that it's not this isn't something new, right? Like right now, talking about EPPS, a lot of people are like, no, we don't even, that's not even compatible with anything we do today. And it's like, well, maybe today, but it's coming, right? And the OCP is already demonstrated, people are doing it, right? And I think that's the advantage of OCP is you get a little bit more faster adoption with it than you do waiting for a standard. But you do still need standards to define certain things. So I think this defining of these pins and the Flex IO concept, very good. But from that, I think the OCP tap group runs with it, right? And that was kind of hopefully is why people invited me to give this talk for this, right? Is to create that type of interest here.
Well, one of the big issues I'm seeing is you defined a solution, but are the people with the problem aware they have a problem?
Yeah,
I mean, a
for
lot of
sure.
these guys don't
Oh
even know
yeah,
if their
we are.
servers are synchronizing.
Yes.
Some of us do, and that's why we
Yeah.
love this.
Yeah, David, that's you, but you're only going to buy so many systems.
True.
You know, this is going out to the big guys and the littler guys where
Yeah.
uh, it affects us, it affects even database speed, in the case of Cockroach and Spanner.
Yeah. No, I agree. I think there's definitely going to be an adoption hurdles, because like you said, some people just they're like, hey, yo, we're running just fine without it. So does that mean we really need it, right? And I think it's like I said, like a lot of those things I was talking about of some of the things you can start doing once you have this in place. I think that's the problem is some people think they're doing it, but they're not really doing it, right? They're close, but they're missing that last hurdle of how do you make it truly work as you want it and make it scalable and make it deterministic, right? So that's the biggest thing is a lot of stuff is right now, as I would say, is more still being very much proprietary, right? Like you could go to Google and they're doing their way, right? You go to AWS, they're doing their way, right? You go to NVIDIA, they're doing it their way, right? So, but over time, they're going to realize it's just not going to be able to keep up, right? They need to find a way that can get access to this, right? Quicker, right? Again, off the shelf components, plug them in, and get people to find these cards that they can just say, hey, yes, I want to start distributing this clock. I don't want to use cables. They're almost just going to affect it, hope it's just already there, right? So I think that's our job is let's make sure it's there for them, right? They're going to ask for it. Yeah.
We hope because they're still not sure they need it. We're selling gasoline, but they don't have a car yet, or they don't know their car runs on gasoline.
We're selling premium fuel, and they don't know if they need it, right?
Build it, and
I'm
they will
running just
come.
fine on regular. There's a bit of knocking every once in a while, but hey, is that really bad?
One of the things I was curious about with Renaissance, so one of the bleeding edge techniques for high frequency trading is trying to make sure that your transmit clock for your FPGAs is using the recovered clock, so you don't have to do a dual clock cross domain. That's just one example of where this technique could be extraordinarily powerful. If you could guarantee your entire data center, not even just rack, is running coherently and then line up the phase, this allows a lot of exciting opportunities. One for reducing latency, but I would think also potentially on the bit error rate, even the rate at which you can clock the SerDes, even reducing noise, etc. I mean, that's why I'm very excited for what you're working with. I'd be curious as well. Have you looked at trying to do this over fiber over a lot longer distances? So obviously there's White Rabbit, but the problem with White Rabbit is it piggybacks on Ethernet. And so if I want to do this, let's say 1,000 kilometers from, I don't know, Boulder, Colorado NIST over a dedicated dark fiber network, is there something we could do here? Maybe that'd be an adjacent project, but is that something you've considered?
I would say there is. Like talk to Julian. He did a concept. He called it PLL over fiber.
Yep.
Kind of interesting. And he was effectively using these modulation techniques. Himself. So
isn't that SDH, Greg, or no?
What's that?
Isn't it SDH?
We're getting there, yeah. We're going to go back to the old SONET protocols and
SDH
protocols, yes. Well, that's why I always laugh when they call it synchronous Ethernet, right? It's like it's not synchronous Ethernet, right? You're synchronizing over the physical layer, but the protocol is still very much asynchronous, right? And that's the problem is you can't take advantage of, even if it is synchronous, can't take advantage of it, right? So like you highlighted, David, hopefully people are going to just, once they get access to it, it's just going to open up a lot of possibilities. And I think that's the thing is this isn't limiting it, right? Like it's trying to make it so it's not limiting. And that's where people may demand classes of precision, right? How good are you distributing that clock? Tell me, right? So that I can actually take advantage of it, right? And things like that.
That was another question I had is how do you define things like rise times, voltage levels, et cetera? And then the other one is if you try to go really down the rabbit hole, even worrying about like switching mode power supplies. And what is the noise? This is one of the things I'm ripping my hair out with now is, okay, can I get something galvanically isolated? And it's like, well, I can, but then I look at the motherboard itself and it has other clock generators and other switching mode power supplies converting. And how do you handle that? And is that something you've seen? Like how well does this work? And at what point does it fail just because of the standard electronics that's trying to, at the end of the day, do a comparator and latch it?
Yeah, like I would say it works fairly well because like we've done stuff where we've actually even put it over coax cable and
Yeah.
played with it that way, right? And we've done a lot of weird things with now, and I've even put out a couple patents on it. Like one is we do one-way synchronous protocol where you actually can use some of the aspects of the reflection to create almost a one path,
Yep.
right? And because you're modulating, you can actually build upon that to say, well, within that modulation, you can actually get the reflection and do
Yep.
stuff with it as well. And so you can create these protocols, you can create a synchronous protocol, you can create a data path. We've done that with our clocks as well. We've created, we can send like time of day information over it. So you can have now in-band communication. So you don't have an out-of-band needs for that. And we've even done complex things like asynchronous clocking to recover an asynchronous clock over that, where the information was all modulated, but
Hmm.
being able to use these markers, you can reconstruct, right? Because you can, like you
Yep.
said, if you know when something occurred at one side, you can recreate it at the other side because you know it's occurring at the same time, right?
Exactly.
And so it's a really crazy stuff you can do with it. Now, not practical with this discussion, but this is just like you said, there, I think people will find that there's things they can build off this over time. Right.
Yes.
So, but I think, like I said, right now the issue is how do we avoid not having to rely on proprietary ways of
Yep.
distribution, and how do we avoid cables? Like,
Yeah.
is probably the fundamental what I'm looking for is let's get away from those cables. Let's just use use the standard connector and distribute the clock using standard clock tree mechanisms, because those have all, like you highlighted, those all have known capabilities where over time you start defining them, right? Like, the slew rate become important? Well, then it'll start becoming a standard, right? That's where the
Yep.
classes might come in saying, I need this type of slew rate on the rising edge because now I'm using the 10 megahertz as part of my precision,
Yep.
not just the marker, right? And so that's part of when I was looking at trying to do it for the ITUT. Their 10 megahertz clock, they talk about a precise edge a bit, but when they talk about
Yes.
distributing just a 1 PPS, they talk about even more about the importance of that rise time.
Exactly.
So I was trying to apply that to say, well, then define that rate as part of the EPPS signal itself, that it has to have
Yep.
the exact same characteristic, because you
Yep.
don't know how they're going to use those other edges in the 10 megahertz clock. So let's just assume they're going to use it the same way they wanted to use 1 PPS, right? So, so I think and that's where defining EPPS maybe where we have a good pointer will be good. So I'm hoping the ITUT will eventually adopt this and define it and put it into the same spec, because that's where we point for 10 meg. It's where we point for 1 PPS. Even though it's talk about going over a cable,
Yes.
the electrical characteristics they define in there are transferable to trace as well, right? You're just going over shorter distances, but the characteristics of the signal, if they're maintained that way and guaranteed, it allows you to do a lot more stuff with that. I agree.
100%. It's something I'm struggling with right now is like you go through the effort of having a rubidium atomic clock that's being conditioned by GNSS receivers, but then it's okay, how well can I actually get that into much noisier electronics, and worrying about the different electrical parameters, slight ripples, and it gets very, very frustrating very quickly. And then it's like, okay, well, where should I be focusing my time to get those next, whether it's, to the nanosecond, 100 picoseconds, 10 picoseconds. And if I have jitter, where's it coming from? How can I get rid of it?
For sure,
But
for
but
sure.
the work you're doing is it's great. I hope it can push this and think about more potentially of how we could do this over fiber. Because like one of the potential ones is we have these national labs with extraordinary oscillators. How can we get that to the rest of the country and not have it locked in or just playing all these games with local oscillators? We don't try to put a power plant in every server. Why did we try to put a clock in everyone in terms of an oscillator perspective instead of just
Yeah,
doing it, maybe twice or three times very, very cleanly?
interesting. Yeah, for sure.
Also, I'm just curious, do you have open source IP cores already that implement this on any of the target FPGA boards?
Uh, there's definitely so the mechanism of doing modulation is open. Like it's in our data sheet. Our data sheet's open.
Yeah,
I've released white papers on it. The concept's fairly open.
it's
The
fairly
only thing that
straightforward, but it's
most
just making
people,
it turnkey.
yeah, I would say it's at a standpoint where it's definitely can be turnkey. FPGAs have done it. We've have some of our partner FPGA vendors have implemented the decoding of sending this modulated signal to it, and they've decoded it and used it. We've even had some of our partner switch ASIC vendors use it, where they're using it as a concept of effectively translating between their mechanism of distributing a time synchronization signal versus a simpler one signal type of thing. They're using it a little bit more advanced because they're actually embedding additional markers in there for data points, but the concept was very much the same. And with all that, they just demonstrated that the fundamentals of like creating clocks or doing other thing else, they could buy any component they want. Even a 20-year-old DPLL can still lock to that 10 meg modulated and generate the
100%. It's basically the unwritten standard in the EE. If you look on the back of a lot of the, there's your oscilloscopes, the signal generator, et cetera. Another one that gets very interesting, you mentioned telco, is on like software-defined radio and beamforming. This is one of the areas I'm very interested in. So then the phase becomes very, very important. If I can lock up multiple SDRs that may only have 2 or 4 inputs and then feed them together. Is that where you're seeing it on the telco as well, or is it more on the wired side? Or
it's coming. So the wireless side does it kind of their own way right now. They do it as a 2 signals. They have their kind of clock, and then they distribute. They call it a sysref, a system reference. But over time, I think they're going to probably adopt this type of idea because, again, the sysref becomes almost it becomes redundant, and B, it then comes down to is you can give very precise phase relationship with that sysref, but then you're responsible for correcting the clock, right? So
exactly,
why can't you just correct the clock with it, right? So that's where embedding it in would probably be better. And
100%.
the sysref effectively, like they're working with about, like instead of 100 nanoseconds, theirs is around 65 nanoseconds, right? That's kind of their cycle they're working with. But that's the thing is you could eliminate these 2 signal things with a single one, right?
That's exactly one of the problems I'm dealing with is even if you provide it like a clean rubidium atomic clock, it then still has its own clock generator or even separate chains of them. And it's like, this is ridiculous. Just get out of the way. And if you try to sync up multiple boards, you can sometimes get this edge case where they're out of phase by like half a cycle. And then you have to do like external calibration or it's a nightmare. And that's why I love this. It's just a potential. Just do it once, do it right, very cleanly, straight into the source so you can synchronize a bunch of other boards.
Yeah. Yeah, and definitely they're trying to do similar things with sysref. I've seen sysref clock distribution and doing the same thing. So effectively, their sysref is kind of like the EPPS. It's just they're not modulating; they're just using a slower fundamental frequency. It's like 7 point some, well, sometimes down to 0.92 megahertz, and they effectively are treating that as its own marker. Each one of those cycles is the marker, right?
Gotcha.
So it'd be like us treating the 10 meg as every cycle is a marker, right? So it definitely, so that's what I mean is it's definitely doable even at the high speeds that you probably could get away with not having a marker, but that's only if you needed to get precisions down to that less than that, right? But the 100 nanoseconds, some says like even telecom, right? They're microseconds still for a lot of their fundamentals, right? So that marker overall wouldn't make sense being based on 10 meg, right? That's why the 1 PPS makes it easier because it's a common multiple no matter how it's being used. Anywhere in the network, anywhere in the user application, right to the radio, it's applicable, right? So that's one of the nice things about the marker being a lower frequency. But 1 PPS, like I said, its predominant was picked because it's just the easiest physical signal to see, and everyone knows what it means, right? Everyone said, "Oh, that's the second rollover," okay, right? But honestly, I would say there's I couldn't even think of an application that needs 1 PPS. That 1 PPS is its fundamental signal.
I can give you one if you want to simultaneously blast orders into many data centers simultaneously to make sure you don't get front run. There's a company called Rentec that I think other people were doing this prior, but they took the patent out. I think it was 2016. And it's like exactly that case as you use it, or sometimes like in avionics control circuits. So this is a concern right now with GNSS spoofing is it messes with the control loops of airplanes because they may do something once a second, once a millisecond, you name it, and it gets disconcerting to say the least. But we do use it sometimes, I promise.
All right, prove me wrong.
So this is absolutely great.
There is no ASIC that, let's say, takes a 10 megahertz, takes a 1 PPS, gives you EPPS. And then let's say it takes EPPS, gives you 10 megahertz, and gives you the 1 PPS. Is there such thing?
There is, but it's probably overkill for that true just muxing and demuxing of the signal. But I would say there's definitely going to be more of those type of devices, especially once EPPS becomes more popular. The idea of having EPPS in and then having a 10 meg and a 1 PPS out, that like, or even any clean clock out and a 1 PPS out, is going to become popular. Where it's not a full-fledged like PLL, where it's more almost looks like a buffer, right? It's a buffer that just takes EPPS and here's the decoded signal, or takes a 10 meg and 1 PPS in and outputs EPPS.
And then I was thinking you can have, let's say, EBPS plus and EBPS minus. Plus is like where the marker is after, minus is the one that's before. And let's say, for example, one of them duty cycle can be like, I don't know, from 50 goes to 30. The other one, like from 50 goes to 60 or like 70. And then with that, you can define, is it ahead or after? Because it really makes a huge difference, like in terms of causality. Let's say you want to just like, as I said, like if it comes before, it's so easy. Let's say I was right away thinking how I'm going to put it, let's say on the time card. I needed basically open the gate, get the snap, and then close. Well, and then when I want to generate it, mess up the signal, generate it, and go. But they contradict, so.
Oh, man, I love that idea. Please make sure that gets a part of something.
But for sure, like I said, like we kind of stumbled on that type of concept because like when we first did this embedding thing, we called it a signature mode, where it was just like at 8 cycles we took, and we just basically each cycle could be 25%, 75%, or 50, which we called a space. So it was like 0, 1, or a space. And we were looking at it more as saying, well, this is a way that you could say, hey, this is a 1 PPS signal marker. Here's a marker. And you could use the signature of saying, this is for you, right? So you could almost give it saying, well, this is only important for this person. They want to care about this marker. But we actually had people doing exactly what you said. They basically said, well, if I just delay it 1 cycle, and let's say my symbol signature is just a 1, which is maybe 75%, and a 0, which is 25%, and then I go all spaces, you could create that exact thing. I could have 1 modulated at 75% just before where 1 PPS is supposed to be, and then the other one at 25%, which is the 1 PPS marker.
It's just like, I don't know, let's say, I don't know.
Yeah.
10
So
times,
it's
10
doable.
times more gates that I need to use, because I'm thinking like, I want to just make it simple,
I think it's the generation of that is more work, right? So that's the thing. But for the distribution and decoding, it's not harder. Like to decode a symbol or decode 2 symbols isn't hard. And to look at 25% versus 75%, it's the same circuit, right? So I think the decoding part isn't the hard part. It's probably more the encoding. Like you said, that's the encoding is probably, even though I call it trivial because it's off the shelf now, not a lot of people do it because it is a lot of work you got to put in, to get the modulation right and to make sure you're not messing up the signal, right? Because like you said, you can definitely mess up the signal, type of thing. So
I have a few questions if there's still time.
Hey,
Great presentation. So I know a lot about your clock matrix parts. So in those parts, you have a distinction between frame pulse and sync pulse. So is the standard planning to be more of a sync pulse where the 10 megahertz edges are actually also disciplined with respect to the 1 PPS?
I would say yes. So it's more of the sync pulse concept. The frame pulse concept to me was more of the telecom. They called it the framing because it was a frame. Basically, it was a framing bit. And so it kind of occurred before the important thing. And so the sync is kind of saying this is actually, we always called the sync pulses actually contain the phase information, right? So that's the idea, is that if the 1 PPS is your sync, which is your phase information, and you modulate it onto the 10 meg, then that means the 10 meg edges have to be the sync or phase information as well.
So you still need a kind of like 2 loop setup like the clock matrix has, right? If you have like a frequency and 1 PPS from the master generation side, you still have some kind of OCXO and 1 PPS source, and then you need like almost a dual loop, right? Because you have to track the 10 megahertz OCXO and then also slowly discipline to 1 PPS.
Exactly. If you're trying to really only use the 1 PPS, that's definitely true. Yeah. Which that's why effectively that's the vision there, is that's probably what's happening in the time card. Most of the time cards, most of those GNSS receivers that you get off the shelf, really what they output is a 1 PPS. And it itself isn't even a great 1 PPS because it's effectively digitally generated off of their TCXO, which is not a telecom TCXO, right? So the thing is there's a lot of variability on that edge over time. So a lot of times that's why you use the CMAX or an OCXO or something like you said locally to kind of get that stability so that over time you can kind of find the average of where that 1 PPS should be and discipline it so that you can generate 10 meg in a 1 PPS or now an EPPS that represents all that alignment. So yeah, so that's why you don't want to distribute the 1 PPS generally, because otherwise you got to put that type of recovery. You know, you may not use a traditional linear closed loop, but even still you're writing something to do it, right? An algorithm or something to try to generate that stability off that and using that 1 PPS as your marker of how well am I doing my stability, right? Type of thing.
Okay. And then I guess you kind of touched on it. You have like this framing capability in the clock matrix parts. Is there any discussion about kind of standardizing that in any way?
I would say probably the short answer is no. Where we find framing historically still being used is still more in the traditional telecom applications and more for those that are still manufacturing like telecom equipment that might be doing still some of the historical Sonnet SDH stuff and things like that. And
Well, I
so a
meant
lot of their systems fundamentally still distribute an 8 kilohertz frame pulse for framing.
I meant the PWM framing where you have like
okay, sorry.
PWM FIFO, all that
yeah,
data stuff.
The signature kind of, I would say yes. Definitely more devices are starting coming out with that. It's already starting in a lot of new product definition is talking about EPPS. So those decoders and encoders will start becoming more popular in clock generators, synchronizers, and even someday probably buffers as well, like that concept of decoding and encoding. The key is we got to create the market, right? So for us, we fundamentally still have to rely on, we want to make money to sell. So if no one's asking for it right now, then it's very hard to justify doing some of those. But some of it we're doing because we know it's coming. Like especially anything to do with using the EPPS coming off the Chem 7 specification, we'll have devices that can lock and synthesize EPPS.
Okay, but people still there's not much market, I guess, for the kind of in-band data thing like that.
I would say no, not right now. I think again, like you used it because I think you eventually, once you find the benefit of it, then you start using it. So this is what I mean is EPPS could evolve. Even probably the EPPS name wasn't great, but I know why it was picked. But it doesn't have to be only the pulse per second that's modulated, right? You can embed other things. So we might have, and then, we had the ETOD for embedding the time of day. We had eData to embed data path, right? Like we created our own little terms off the E for embedding stuff onto the thing, but the idea is the same. You have a carrier and you're modulating the signal to create it. And the more complex it gets, then the more coordination you need, right? You have to define like concepts of headers. It effectively becomes a protocol, right? So you would have to generate that interest because to keep it too flexible is costly, right? To keep it to say use any header and decode any header type of thing, it becomes a little bit more. But if people start saying, hey, I'd love to distribute data over this, over fiber and distribute information along with that marker, yeah, that'd be great if it becomes more that basically all these NIC cards, you want that capability to decode that information and use it. Then
I know it's possible with your chip because I did it, but it's very limited throughput, especially. So yeah, it's not an intended use case per se.
Exactly. Well, that's the thing is it's meant to be still kind of a slow protocol. Like you ran, I think, at 25 megahertz or something, right? So it's
Well, but the data throughput is much lower. I think it was
exactly because that's the thing is that's 25 megabits, which is still, but I think we put it into chunks of let's say 200 bits. So one packet of information, you can't send a lot if you divide that up over a 25 meg slice, right?
Right.
That's why fiber and everything is going. What are we now at? Like 1.6 terabits per second, right? Like when you get to 448 gig and do it in multi-lane, right? So yes, it's not meant to be a replacement of a, replace Ethernet. That would not be the intent. I would say it's more for the concept that Dave was highlighting, like maybe like a dark fiber or, sending a synchronization signal over fiber could be definitely done. But we're typically talking at rates. I think we ran those max up to like 40 or 50 megahertz because, like I said, it just becomes difficult, especially if you're trying to send different types of information on it, right? If you want to try to send a precise marker plus the information associated with that marker plus effectively asynchronous data, there's a lot of coordination you have to start doing, right?
Yeah.
Very similar to Ethernet when they started looking at trying to do prioritization, but they tried to look at how can you do maybe like fast FIFOs, right? Where you interrupt something that could be happening to send very important information right now, like this second. That sort of thing adds complexities, which it's not that it can't be done, but I think finding a profitable market for that is not gonna. You could probably do it with an FPGA just as well, and we'd probably just say go get an FPGA and play with it.
I had another kind of related question, if you don't mind.
Sure.
Is there any discussion about making this kind of bus like? I mean, there's a lot of like bidirectional interfaces out there these days, or even like CAN bus or EtherCAT has some kind of sync frequency distribution, and it's like low speed data, also that kind of stuff. But and I mean, even Ethernet 1 gig base T is fully bidirectional over the same diff pair, right? Is there any investigation about? I mean, like, because these EPPS signals are just like LVCMOS. It's nice and simple, but for kind of a bidirectional interface, it gives you the ability to do full round trip measurement, and you could just define like one diff pair gives you time in and time out depending what you do. Is there any kind of discussion about that?
I would say not right now. There's not a lot, like not in the OCP, let's say. Like I said, like the telecom guys, a lot of them are doing their things, right? And they still are. In terms of like clocking and synchronization advancements, they're still the leaders. It's why you heavily see references back to telecom because they've been doing synchronization for a very long time. So for the OCP, I think it's always what you see a lot of times people will present something trying to relate it to telecom and say, oh, you should just do the same. But this is where sometimes it doesn't make sense because the OCP to me should find, well, if there's history, we want to skip the history and get to the good stuff, right? So to me, that's what the EPPS was. It's kind of like, as they've highlighted, like the concept has been around, 10 megahertz has been around, even the 1 PPS has been around. But they're slowly also converging to EPPS. But why, why introduce all the old concepts to the OCP community, right? And it's the same thing when they talked about like doing network synchronization, and they talked about, wow, telecom used to have a frequency synchronization, and then they had a phase synchronization, and so they had to be independent domains. And I'm like, why are you complexing this? OCP has nothing, so just give them a synchronization, a network synchronization just running. Like don't bring the history in if it's not needed, right? Learn from it and then apply, right? So that's where stuff like, the 1588.1, saying, hey, let's apply how to use 1588 over to get a common synchronization network, right? I don't care that telecom needs two, right? And some dedicated telecom server can handle that. But for the general concept, I just want synchronization distribution. Let's come up with the best method using what we use today, right? It's got to be layer 3. It's got to be transparent. It's, whatever, right? Boom, 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 boom. Jump ahead, right? So I think that's the thing is because of that, I would say it also is being driven, but you have to know what you want. Like if you have a need, then it'll get broad. But if no one's asking for it, it's hard to bring, right? So I think that's the fundamental thing is it's hard to bring it because they're just like, right? Or they just like, well, telecom does it, but that's because telecom does it, and it's their application. We're not telecom. So,
Yeah, that's the chicken and egg problem with all of these things. But yeah, thanks for
exactly.
answering the questions. Yeah.
Yeah.
All right, I think you broke the record of the longest talk. So
Yeah, sorry about that. I was
think
not
last
intending
one
for
was, I
that.
think, an hour 48 minutes. David, go for
I
it.
get two more quick ones. Just
All
something to
right,
think
go.
about.
Let's get to the 2 hours.
Yeah, let's make it hard to break, you know.
All right, perfect. Yeah, so I think it was Hank was mentioning like, can you do things like measuring, and there's different techniques you can do, like reflecting different signals. But another one to think about, and the price on these is really plummeted, is you can get DWDM optics over a single fiber, and there's a frequency dependent coefficient of the speed of light in the cable. And so you could actually take advantage of that if you sent the same signal multiple times just by receiving it one way, despite what one of Ahmed and I's mutual friends, Paul, thinks. It is actually possible to measure the one-way speed of light in a fiber optic cable if you know the index of refraction. And so you could potentially take advantage of that. The other one, you're talking about some of the low bit rates. The one thing for me that this is perfect for is for getting the output of GPS receivers. So you mentioned like encoding the exact time of day, but also some of these other signals like NMEA or like U-blocks and others have their own proprietary bit rates. They do tend to be relatively low bit rate. Often we run them over serial, and you're only doing sometimes even 960 baud or maybe a slight multiple of that, but we're not talking gigabits of data. And so there, it seemed like a natural one to finally have a single cable to get all of this. To me, is enormously exciting instead of having to worry about USB serial, UARTs, external 10 meg, external pulse per second. If you could just get it all into one, I think there could be a lot of cases that makes that very clean.
So,
Yeah, I agree.
sorry, Greg, just to add to David and Julian's comment, I did some like an unrelated project where I encoded over an embedded PPS, a similar thing with a 4B, 5B encoder, and basically it was an 8 megabit, and what it carried all the time of day, or even basically a serial IP over nodes that I needed to actually carry information. And that was exactly what you were mentioning, David, about having all these cable for this application. They wanted to basically distribute all these signals plus a bunch of control channels that they didn't want. Actually, the reason was quite a few of the equipment had different physical layers that they needed to cable through each and every one, each and every node. And basically it was easier because it wasn't an ASIC, so it's an FPGA, and you can encode it, and it's actually pretty easy to do and very low cost in terms of the amount of LUTs you can encode in an FPGA. But it's like you have an 8 megabit channel going from every node, and we used the fact that it's bidirectional in this application. It wasn't just unidirectional. You could actually do calibration and round trip child measurement because you have a clear channel of data that you can do whatever you want with it. And it's basically deterministic. You know that you have 8 megabit of channel going from every endpoint in the design. But it was a specific application. I don't know how general purpose it would be for other people.
More than you'd expect. I think there's a lot of us all doing the same thing, and we just accepted that we had to put up with different cables and protocols and everything else. So that's
maybe there is a need or a usefulness for, so EPPS would be, so what Greg was doing, and thanks again, Greg, for a very nice presentation. Like in terms of at least having all the electrical spec and everything like that standardized with ITU or somebody else, and having that as basically the electrical layer and the physical layer. And if you have to piggyback a protocol on top of it, it's trivial. But the problem with triviality is like there would be 600 different trivial applications that would encode it. So maybe a follow on, if we can gather the information of why this thing is useful and what people want to get out of it, then we can, like, there is so much from previous stuff that we can draw on and we can make a single proposal that hopefully will address a lot of this, so no one gets to reinvent the wheel. Sorry, go ahead, Greg. Sorry to interrupt.
Oh, that was great.
No, that's fine. I think we're nearing the end anyways, because I already see warnings popping up saying recording is going to stop in 2 minutes anyways. So
Speaking of time,
yeah.
we did it. Hey.
All right.
Yes,
Great.
probably. I don't want people to also see this video and see, 2 hours. Oh, I'm not going to sit through that. So hopefully you put down on that it's only 1 hour, 55 minutes.
No, we'll compress it. You know,
You just run it at 2x speed. It'll all be
Yeah,
good.
exactly. That's what
there
Blame
you go,
GPS
yeah.
spoofing.
I'll sound like a chipmunk. And yeah. All right. Well, I appreciate everyone's time and thank you for listening. And hopefully it sounds like you guys found it informative. So I appreciate the feedback.
Thanks, Greg. Very interesting.
We appreciate your hard work. Just keep it up. You're a great firm, and we love what you're working on. This would make my life personally so much easier. So thank you.
Good to hear.
We'll see everyone in 2 weeks by a presentation from Andreas Hildebrand about precision time requirements in media of IP. All right.
Sounds good.
We'll see everyone.
Sounds good. All right. Thanks, everyone.
Thanks.
Bye.
Bye.